Our last presentation for this session before the break is from Martin Landrø, talking about the Lunar DAS project. Martin, take it away. I'll let you know when you've got about 2 minutes left.
Thank you, Caroline. So this is a joint project between NTNU and DLR in Germany. So to put it into some context, this is a part of the EL3 proposal, and it's the main mission for this is to study the potential to detect polar ice by using DAS. And it's a combination in this project. It will be combined by the GPR, ground penetrating radar system, and magnetic induction spectrometer and DAS. So we have 3 different tools that we propose in this. Stavros has explained this in the previous talk. So DAS interrogator is a laser source that exploits the backscattering in the fiber. And of course, the nice thing about fibers is that they are light, so it's not too much weight. The interrogator, which you see here, weighs 19 kilos. I will focus on some examples from Earth, or actually from subsea. 2 years ago almost, we recorded for 40 days DAS data on a fiber that connects 2 small cities on Spitsbergen, Ny-Ålesund, that you see up here, to Longyearbyen. And we recorded a distance of 120 kilometers of this fiber. To the right here, you see a mid-Atlantic earthquake, and you see how the data quality degrades with the distance. This is distance from 0 to 120 kilometers. And this is the P wave arriving at the sea bottom cable, and this is the S wave coming later on. What has happened with the DAS during the last, I would say, 4 to 5 years is that the sensitivity has been increasing by several factors, several magnitudes, which enables more and more detailed investigations. So to the left on this slide, we see a normal cargo ship crossing the fiber, and this is the fiber is here, the black line that you see here, and it's crossing at approximately 86 kilometers from the interrogator, which was placed in Longyearbyen. So it's a long distance. The gauge length was 8 meters in this experiment, so we have very dense data. So the red line is the AIS data from GPS or from the ship, and the white dots are overestimates based only on the acoustic signal that was measured by this fiber optic cable at the sea bottom. And we see that we fit pretty well. There are some outliers here and there. We even see the well-known Doppler effect. So when the ship is moving towards the fiber, it has a slightly higher frequency than it moves away from the fiber. It's 0.25 hertz. You also get an impression of the noise level here. To the upper right, you see whale calls. So this is they look like hyperbolas. So again, you have distance along the vertical axis here and time, approximately 1 minute along the horizontal axis. So what we see here is several whale calls, and close to this red line that you see here, you have another whale. So these whales are separated by approximately 2 kilometers. We can perform vocalizations of this based on the DAS data. So if I'm able to cross here, that was not possible. Let me see. It should be possible to play this sound. No, that didn't work. But it's quite nice to listen to the whales. We can actually record the whale callings and play them back as sound files. And that's quite amusing to hear. So what we see here is the spectrogram of a blue whale call, and we see several of them here. We can even do better. We can make seismic shots of this by using interferometry. So to the left here, we see one whale call that is at a distance of approximately 25 kilometers, and another one that is at 87 kilometers. And then we can identify the direct arrival, but also reflections from the subsurface. So this is approximately 100 meters below the seabed. And you notice that when we go out to 87 kilometers, this first reflection is getting closer. So it tells us that the first this layer is thinner here than at 25 kilometers. So in this way, we can start to use this, the blue whale as an active source. Then I want to show you some example from a clay area we have studied close to where I live. It was a big clay landslide in 1978. 7 farms were washed into the water, into the sea. And today they're building a new road here. And then we installed fiber optic cables and used DAS experiments to monitor the shear wave velocity in the clay. So that's the purpose of this. What I want you to notice here is the signal from a person walking. That's what you see here. This is a person walking along the fiber. It's time along the vertical axis and distance along the horizontal axis. So it's 300 meters. And then we made a shot by a sledgehammer here, and then you see a much stronger signal. So it's interesting to see, to compare these two signals, that of course when you use a very active source, you get a much stronger signal that propagates in the earth. But even a person just walking on the surface makes quite a detectable signal. We detect shear wave reflections from this in this shale, and we are able to see both reflections and a lot of refractions that we use to determine the shear wave velocity. So then we want to use this quick clay experiment as a proxy for lunar DAS experiments. We have made clay measurements, and we know that it's a huge difference between clay, of course, and the lunar environment. There is, however, one similarity. The shear wave velocity in clay is around, say, 150 to 200 meters, and then you have a strong bedrock below. There are some papers using data from Apollo 17, where they measure the shear wave velocity in the regolith layer to be around 100 meters per second. So the shear wave velocity of the shallow subsurface of the moon is similar to what we have in our field experiment. So that's what we think is similar. But of course, there are a lot of differences also that we have to be aware of. Dry ground, for instance, presence of ice. The clay is kind of homogeneous, so there is no ice in the clay, and there are a lot of different things. So this is what we propose, is to keep the interrogator in the lander. The interrogator needs to be protected and at a constant temperature, and then to use the rover to deploy the fiber into the shallow region. And of course, then the fiber needs to be handled with care. And then we suggest to use the rover itself as an acoustic signal, similar to when the person is walking close to the fiber, as I just showed. So that's just focusing on, maybe we have to kind of look into how to create as much shear wave energy as possible. Maybe we have to look into how the rover can be designed, or the wheel of the rover can be designed to optimize the amount of shear wave. So then, to summarize, the opportunities as we see it, and what was also pointed out by Stavros in the previous talk, is that we think that this can be used as a direct geophysical detection of ice, water, resources, and seismic mapping. We think it can be used also for a massive multi-channel recording of moonquakes and other passive seismic observations, of course. Challenges, more challenges than opportunities maybe on this slide. How to deploy the fiber. That is a critical phase, I think. Weight of the interrogator is 19 kilos presently. We are looking into how that could be reduced. We need a data processing unit in the lander. And of course, to create a 3D layout of the fiber is also a challenge, but we think it's possible. And of course, the using of the rover as a seismic source, that is also a challenge, how to design that. And of course, absorption, scattering effects, etc. on the seismic data. So then I think I stop there. Thank you.
Okay, thank you very much, Martin. We do have a question for you in the chat from Bernard Foy. He wrote, did you look at testing the DAS system at Etna pyroclastic ash deposits, which is the site of the DLR Arches campaign from the 13th to the 30th of June?
Yeah, I have discussed that with Nicole Schmitz. So that's I think that's a very good idea, because then you get a totally different environment than the clay that I showed in this presentation. Yeah, so that's a good idea.
Right. Yeah, and because I guess maybe, you know, the concern there would be as if the water content makes it much easier to get signal compared to the drier sort of then, yeah, pyroclastic type materials, regolith type materials that you would have on the moon.
Yep, that's a good point.
Yeah, Nicole Schmitz just wrote that, yeah, she also had mentioned that to Bernard.